Okay, hey everyone, welcome back. So we are going to travel outside of our galaxy, the Milky Way, to look at properties of other galaxies. So I think the first thing we need to appreciate is that the field of extragalactic astronomy is only about 100 years old. Most of the time humans have been doing astronomy, we had a really hard time measuring distance. There were, discussions back and forth, but we kind of assumed that the universe was one galaxy, right? It was the Milky Way. The Milky Way was the universe, and the universe was the Milky Way. So in the early 1900s, Henrietta Leavitt of the Harvard Observatory realized that we could use these special types of variable stars called Cepheid variables to calculate distance. And she determined that the period of these Cepheids, the time it took for them to brighten and dim, was related to their luminosity, right? Their intrinsic brightness. So once we know how bright something is, we can compare it to how bright the thing looks, and we can find the distance. So Edwin Hubble used this relationship, this what we call Leavitt's law, to determine the distance to Andromeda, which at the time was known as a nebula, just a big mass of gas and dust. So the actual distance he found was kind of way off by modern standards, but he showed that Andromeda was way further away than we assumed, much further away than could possibly be inside the Milky Way. And he proved that Andromeda was, in fact, its own galaxy. So, what we often do when we first discover something is we try to classify it by its most obvious characteristics. And in this case, that would be classifying galaxies by their morphology or their shape. So, there are three kind of general morphology types in galaxies. The first is a spiral galaxy. So we talked about spiral galaxies a lot when we first discussed the Milky Way because the Milky Way is a type of spiral galaxy. It's a barred spiral. So the main physical characteristics of a spiral galaxy is that central bulge and or a bar, the halo, the disk, and the spiral arms. Spiral galaxies tend to have new star formation in the dust and gas in between the stars in the disk, and especially in the spiral arms. There are open star clusters, so kind of loosely bound associations of stars in the disk, and globular star clusters in the halo. And globular star clusters are kind of more massive, more tightly bound together. Spiral galaxies contain young and old stars, and it rotates, right? That's kind of what makes that spiral shape. Nearly two-thirds of nearby spirals have a bar, so we do think that bars are pretty common and pretty long-lived features in spirals. The mass of these galaxies range from about 1 billion to 1 trillion solar masses and can range in luminosity from 100 million to 100 billion solar luminosities. And they can vary a lot in extent. So the diameters can go from 20,000 light years to well over 100,000 light years. And that's not to mention at all their dark matter halo. So these are just some examples of spiral galaxies. On this side, we have NGC 1300, which is a barred spiral. You can see kind of this bar in the middle. Right here, NGC 1232, which is kind of more of a classic spiral, the bulge in the center, and these beautiful spiral arms. Spiral galaxies can be further subdivided depending in part on like the tightness of their spiral arms. So you can have SO galaxies right here. These are lenticular galaxies. This is more like just a pure disk, really, not any spiral arms. Oops, let me go back. Sorry. Then spiral arms can be classified as SA, SB, and SC, kind of depending on how tight these spiral arms are. SC have a mini spiral arms that are pretty loose. SA, they're pretty tight. If we have a barred spiral, we kind of have the same type of thing, loose spirals to tight spirals. but they have this bar in the middle, and their classification is just SBA, SBB, SBC. The second type of morphological category is an elliptical galaxy. So these galaxies are made up almost entirely of old stars. The stars in the galaxy also have random velocities. So stars in spiral galaxies kind of more or less travel in the same direction. So that gives them like a really organized disk shape. Not so with ellipticals. Stars are kind of going in random directions, which gives elliptical galaxies a spheroidal shape. So this is an elliptical galaxy kind of in the background here, and superimposed are just some like example trajectories of stars. And you can see they're kind of all over the place. They're not going in kind of a neat circle. Spiral galaxies have a lot of dust and star-forming regions that are called emission nebulae. Ellipticals do not have a lot of dust and gas floating around, and we don't see those emission nebulae either. There's not a lot of star formation going on in elliptical galaxies. Elliptical galaxies can also be some of the most massive galaxies in the universe. They can get up to 10 to the 11 to 10 to the 13 solar masses with diameters of several 100,000 light years. But at the same time, ellipticals can be among the smallest galaxies. So these are dwarf ellipticals, and they can have the luminosity of basically a big globular cluster, which for a galaxy is actually quite faint. The last general shape a galaxy can take is kind of a catch-all category. We call them irregular galaxies. Like the name implies, these galaxies don't have a regular shape. Uh, these galaxies have lower masses and lower luminosities than spiral galaxies, and they really have a disorganized shape and appear to be going through an intense bout of star formation. And good examples of this are the large Magellanic Cloud and the small Magellanic Cloud. Like you can see they're kind of bluish, which would indicate some star formation, but they don't really have a very organized shape. A lot of galaxy evolution is driven by mass. So it's important to be able to calculate that. Um, we have talked about how to calculate the mass of a spiral galaxy using Kepler's third law in the Milky Way lecture. So I won't revisit that here. If you want to review, you can rewatch that lecture. It's a bit more complicated for ellipticals, though. For ellipticals, we need to get the spectrum of the galaxy. So we can't measure rotation of an elliptical like we can a spiral, because remember, all of those stars are kind of going in random directions, but we can measure the movement of those stars. And that movement will cause a Doppler shift in the spectral lines, sometimes towards the blue and sometimes towards the red. A galaxy spectra is nothing more than a composite spectra of all of the stars that are in it. So we can look at that spectra and see the Doppler shift. Um, and we will notice that that Doppler shift makes the spectral lines look broader. So this is called line broadening. This is just a cartoon of kind of what that looks like. So if we normally would see a very skinny, maybe emission line at some wavelength, the Doppler broadening will make that line look a little broader. The broadening indicates the range of speeds relative to the center of the galaxy, and the range in speeds depends on the force of gravity holding that galaxy together. So with this information, astronomers can calculate the mass of elliptical galaxies. Another way to determine mass is to find the mass to light ratio, or M over L. So it's the ratio of galaxy mass measured in solar masses to the light emitted measured in solar luminosity. So if you remember the HR diagram, most stars are less massive and less luminous than the sun. Most stars kind of live down in this area. And so these stars here are going to make up most of the luminous mass of the galaxy. So they will provide a lot of mass, but since they're small and dim, they won't provide very much light. So the mass to light ratio for low mass stars is greater than 1. And so since these are most of the stars in galaxies, the mass to light ratio for a galaxy will also be greater than 1, but the exact number depends on the exact ratio of low mass to high mass stars. So galaxies that are forming stars will have many massive stars, and their mass to light ratio will tend to fall between 1 and 10. Galaxies with an older stellar population with few massive stars will have a mass to light ratio between 10 and 20. So this is important to remember, though, that this applies to normal matter that we can see. We'll talk a little bit more about the mass to light ratio when we include dark matter in a later lecture. Distances are also an important thing to measure with galaxies. So how do we even measure distances to galaxies? And there are, several ways. Your book draws attention to a couple of the big ones. So we talked a little bit about Leavitt's law and how we can use Cepheid variable stars to calculate distance. We can still do that. We've refined that method over the years, so it's even more accurate. Um, Another way to calculate extragalactic distances is through the use of what we call standard candles. So a standard candle is a phenomena that gives off basically the same amount of light every time. And once we know what that amount of light is, we can calculate distance. So a popular standard candle is a type 1a supernova. So these are white dwarf stars that have siphoned off enough matter from a companion star that it gets massive enough to explode. So these stars reach kind of nearly the same luminosity at maximum light, and they can be seen from about 8 billion light years away. To be technical, though, and accurate, these are really what we call standardizable candles. There are some subtle differences between different type 1a supernova, but it's so well understood that we can account for these differences. So kind of on the screen here, this is how astronomers do this. This is kind of a distribution of different type 1a supernovae, but once we kind of apply the correction, they all pretty much fall on this curve here, which makes it very easy to use them to calculate distance. Another way to measure distance is by using something called the Tully-Fisher relation. Be warned, though, this only works for spirals, and you will see why in a second. So it turns out that the luminosity of a spiral galaxy is related to its rotational velocity. The mass to light ratios for spirals are fairly similar, so we can estimate luminosity by measuring mass, and we can estimate mass by measuring the rotational velocity. Put another way, measuring the rotational velocity of a spiral galaxy can give us a good estimate of galaxy mass, which we can use to estimate the galaxy's luminosity. And once we know the luminosity, we can compare it to how bright it looks to us and get the distance. So this method only works for spiral galaxies because we need rotation, but there is a similar in concept method for elliptical galaxies called the Faber-Jackson relation. So it uses something called velocity dispersion instead of rotational velocity. And velocity dispersion is just a way to quantify that line broadening that we discussed earlier. So here are an example of some plots with galaxies. We have Tully-Fisher on this side and Faber-Jackson on this side. And so you can see a positive relationship between the luminosity of the galaxy in both Tully-Fisher and Faber-Jackson with the rotational velocity for Tully-Fisher and the velocity dispersion for Faber-Jackson. The Faber-Jackson relation gets used with elliptical galaxies. Tully-Fisher is used for spiral. The last topic I'd like to hit on for this lecture is how we know the universe is expanding, right? The discovery of galaxies and the discovery that the universe is expanding kind of goes hand in hand. So prior to Hubble's discovery that these faint smudges we saw in the sky are galaxies, astronomer Vesto Silfer measured the spectra of spiral nebulae, which were what galaxies were known as at the time. So he noticed that their spectra had a pretty large shift to the red, which means that most of the galaxies he looked at were moving away from us pretty quickly. No one quite knew what to do with this information. We didn't even know what galaxies were when he made these calculations, these observations. After Hubble made his first discoveries of galaxies outside the Milky Way, he worked to make his distance measurements more accurate, and he measured the distances to Sulfur's galaxies. Hubble plotted that data and noticed that the further away a galaxy was, the faster it was moving away. So this is the plot from his paper at the time. We have distance and redshift. And what this indicates is that the the galaxies that are furthest away from us are actually moving the fastest. So this is really incredible and is considered the first observational evidence for an expanding universe. And it's encapsulated in a fairly simple equation, right? It's V equals H times D, where V is the recessional velocity of the galaxy, right? How fast it's moving away. D is the distance, and H is the Hubble constant. It's not really constant, though. H seems to vary with time. So you may see this equation as I have it on the screen, replace H with H naught, so we call it, which represents the present day value of the Hubble constant. So this is called Hubble's law, or if you will pardon my butchering this name, the Hubble-Lemaitre law. So the book says that astronomers are converging on a value for H, but I think that's a little bit misleading and kind of untrue. So in fact, the value of H is one of the biggest problems facing astrophysics today. It even has a name, right? We call it the Hubble tension. So well, there are a lot of different independent ways to measure the Hubble constant. Um, we get values that are relatively close to each other. For a long time, the errors on these measurements were large. So we assumed that as we cut down on the errors and got more precise measurements, we'd find that these methods would give us the same value, um, which if the Hubble constant is truly constant, they should converge, right? But they haven't yet. The errors are getting smaller and smaller, but we're still getting different values. And this is really important to figure out because we'd love to use this method to calculate distance. Um, it's not dependent on our perception of light or anything like that. We still use it to calculate distance, but we all kind of know that this is based on a certain model of the universe that may turn out to be wrong or at least incomplete. So really resolving the Hubble tension is actually one of the biggest research areas in astronomy. Okay, so studies of type 1a supernova have shown that not only is the universe expanding, but the expansion is accelerating. And it appears that everywhere in the universe is moving away from us. So this kind of brings up a question, are we actually the center of the universe after all? Were the ancient Greeks, were they correct thinking that the Earth was the center of it all? The answer to that is no. This just indicates that space is expanding uniformly at the same rate everywhere. I really liked this ant on a ruler example from your book, so I want to go over it with you right now. So let's imagine like a ruler, like a stretchable ruler, with kind of the usual lines marked off at each centimeter. So now think about someone grabs each end of the ruler and stretches it so that it doubles in length in 1 minute. So let's say that we have an ant, right, sitting at the a mark at 2 centimeters. So it's a point that's not at the end or the middle of this ruler. So he measures how fast other ants sitting at centimeters 4, 7, and 12 move away from him as this ruler stretches. So the ant at 4 centimeters was originally 2 centimeters away from our ant, and he's doubled his distance in 1 minute. And so he has moved away at a speed of 2 centimeters per minute. The ant at 7 centimeters, which was originally 5 centimeters away from our ant, is now 10 centimeters away. And so he moved 5 centimeters per minute. And the ant that started at the 12 centimeter mark, which was 10 centimeters away, um, is now 20 centimeters away, meaning that it must have moved away at 10 centimeters per minute. So the ants at different distances move away at different speeds, and their speeds are proportional to their distance, right? Just like Hubble's law, predicted or indicated with galaxies. But notice in our example that all the ruler was doing was stretching uniformly. Also notice that none of the ants were actually moving themselves, right? It was the stretching of the ruler that moved them apart. So this is pretty wild to wrap your mind around. And this should only be considered kind of a conceptual example. The real universe has no edges, right? The universe, as far as we know, is everything and it's expanding, right? It's a lot to take in. So it's a lot to take in, and I will kind of leave us here with this mind-bending ending to the lecture. If you have any questions, shoot me an email or stop by my office hours.